This is the last video for this week, and you see that what we had in our interactive syllabi for this week, calculus with power series. So finally we are coming to that power series. So let's see. So power series is a series of functions. So we simply write down an infinite polynomial, and that's it, right? So it's exactly what we found the exponential function e to x was. And power series have got very fantastic properties. So we say that the series S has got a radius of convergence rho if it holds true that the sum converges for all x within the disk of radius rho. Therefore it's called radius, right? It counts with complex numbers. We shall deal now with only real x's, but essentially there is no reason why to object if you want to throw in complex x, because it will be just polynomials with growing order, and it works with complex numbers equally well. So we say that Sx is radius of convergence rho if it converges for x inside of the disk with diameter rho, radius rho, and it diverges for strictly bigger absolute value of x. So that's the convergence disk. And now there is the fantastic theorem. So whenever you meet a power series, you can compute the number r, which will be the Limes superior of the nth root of the absolute values of an. So this comes from the root ratio test, right? And which we discussed for the individual coefficients. And then the radius of convergence of our series is the reciprocal value. So equivalently, we may also do the same with the ratio test, not the root test. So that gives you also the explicit number r, and the reciprocal value of r gives you the radius of convergence. And the power series converges always absolutely on the whole radius of convergence, and it is continuous on it. So it's always continuous on the whole. And actually it's true that it's continuous including the boundary points in which it might converge. We don't know whether it would, but it might. And the derivatives of f of s exist on the whole convergence interval, and and it's computed as we know from the polynomials. So we simply are allowed to interchange the two limit operations, the summing of the series and the differentiating the terms, right? So we differentiate first the terms, then we sum the series. So you can also read it in such a way that taking the formal derivative as with polynomials, we get a power series which has got the same convergence radius, and on all the disk of the convergence we know that actually it's the derivative, right? So that's a very great theorem, and it will follow automatically from some more general properties of series of functions we come to in a couple of weeks. But I advise all of you who love to read the proofs to go to the 6th chapter and see how the whole thing works for complex x's. No, wrong. In the 6th chapter, it's what I mentioned to come in a few weeks, but I advise to go for a direct proof, which is just about 1.5 page proof in this 9th chapter, where we deal with the complex setup. There the x will be allowed to be complex, and we shall have a extended version of what the derivative is, and it will still hold true. In a special case, all the proof can be read just for our real case, and it's a quite simple series of estimates, much simpler than what I was showing you with, well, but not explaining with the exponential function e to x. right? So that's the main result about power series. And now let's have a look how the power series work, right? So I already showed you one that was the geometric series, that's this one. And we know that the geometric series has got this value. So you immediately see that the geometric series can only converge for absolute value of x less than 1. To have some other example, imagine you have got something like 1 over 1 plus x squared. So that's always a question whether this could be written as some an x to n for n equals 0 to infinity, right? And we shall see soon that it is possible. But whatever you do here, you can't expect anything different as the convergence radius as to have it only 1, because it must work for the whole complex plane. And if you plug in I here, so you see that I squared is -1, so it explodes to infinity. So the power series can't have a bigger convergence radius than 1, right? So that's just to see the beauty, to understand things in the wider sense as living on the complex plane, because otherwise it's hard to explain why such a thing couldn't be given by a power series which would just converge further, right? So that's what I wanted to say. And now let's have a look. Let's have a look what we can deduce from our understanding of e to x, right? So just remember that e to x is 1 plus x plus 1 over 2 factorial x squared plus, and here would be 1 over k factorial x to k plus up to infinity, right? And now imagine we plug in the purely imaginary things, right? T is in R. So what we see is that e to it, it will sit on the unit. So here is I, here is 1 unit circle in the complex plane. And therefore you see that from our definition of sine and cosine by a picture, so this will be a point with coordinates cosine t plus I sine t, right? And this is exactly what we can see. We can also see that it's quite easy to check that the rule we use to define the e to x plus y in the real line will hold true also for the complex, for the power series. It's just some combinatorics looking at how the terms are, right? So and it will use our knowledge how to work with products of the series. So that's a nice exercise to check that this holds also for the complex plane. And now you can see that writing down the ET, you have got the real component and the imaginary component, and they correspond to the sine and cosine. So we see immediately that we can compute what the series for sine is, and we can use what the series of cosine is. We can compute the derivative and look at the derivative, and we see that the derivative of sine is cosine, and the derivative of cosine is minus sine, etc. We can also compute the trigonometric equations. We see immediately that the sine square plus cosine square is 1, and all the things are computed quite easily and in a straightforward way, like this kind of formula, and so on, right? So the tangent, cotangent, everything is computed in terms of power series. So now I can say that the sine and cosine are not only well-defined functions by a picture, but they are computable. They are computable via the power series. and there should be a picture somewhere, not here, somewhere else. I had a picture how many terms you have to compute to approximate your say sine or cosine nicely, so it will come somewhere else. Right, of course, the final comment on the power series, you can easily also expand power series in some different points. So you simply, instead of writing it as x to power n, you write x minus some center x0 in power n, and everything holds true as before, right? It's just the disk of the convergence with radius rho will be then around the point x0 instead of elsewhere. And you can also use some combinatorics to compute the inverse functions. So I think so. So here you see how we did this Arcus sine. I guess somewhere I also computed the power series for the logarithm. Here it is, perhaps. Yes, here is the power series for the logarithm. And from the power series of the logarithm, you see that actually if you have logarithm of 1 plus x, then it's something which is as I used when I derived the properties of the exponential function. So this is very rough image, very rough introduction. So I hope you will enjoy playing with power series a little bit, and do it please, because power series are the core of computational powers, right? It's also very powerful for combinatorics and for estimates. So in data analytics, you will definitely find power series. So thanks for attention in this whole week.